Now we'll continue with the second part of Part C, urine production. Here we'll look at reabsorption and secretion and briefly at diuretics. We have finished with filtration. Now let's take a look at reabsorption and secretion. We lump these together because the mechanisms of both are the same. Remember, 180 liters per day is filtered from the kidneys, and fluids filtered into the tubules may eventually be excreted. But here's a question. Do you excrete 180 liters of urine a day? Obviously, no. How much blood does an average person have? Answer, you have roughly 5 liters of blood. If you filtered and lost 180 liters a day, you would lose all your blood in a very short time. So, most of the fluids that are filtered are returned to the body by reabsorption. Reabsorption controls fluid composition. It leads to retention. Useful substances are returned to the blood. Roughly 178 liters per day is reabsorbed. That leaves roughly 2 liters a day to remain in the tubules and excreted as urine. It's a bit less than that. Secretion adds additional substances to the filtrate. This includes penicillin, potassium ions, ammonia. What about the mechanism for reabsorption and secretion? Well, it involves both passive and active transport processes. Concentration review. I know we've covered this already in the cell unit, but it won't hurt to go through it again. The term concentration, remember, used alone refers to solute concentration. The phrase water concentration refers to the concentration of water. Sometimes it's convenient to refer to that. Net means a difference. Consider particles moving in two directions. If more are moving to the right than to the left, the net movement is to the right. Passive processes, you may recall, include diffusion, osmosis, dialysis, and facilitated diffusion. Much of this will be a review of the subject of transport in the cell unit. Osmosis, dialysis, and facilitated diffusion involve a selectively permeable membrane. Such a membrane allows certain substances to cross and prevents others from crossing. Let's look at the first of the passive processes. This is diffusion, the movement of particles. I don't like to include in the definition from low to high concentration or something similar. Let's add, however, with a tendency to become evenly distributed. The concept of net movement will be explained shortly. Osmosis is the diffusion of water through a membrane, shown in the figure. There are no such things as water carriers. Water molecules are small enough to pass through the lipid bilayer. Also, there are water pores, aquaporins, that allow water to cross. For convenience, we will think of the membrane as having holes in it. Note that water crosses in both directions. Dialysis is the diffusion of solute through a membrane. And facilitated diffusion is dialysis using a carrier. A carrier protein would transport the solute particles. For example, the solute binds to the protein flips to the other side, and releases the solute particle. Passive transport has certain characteristics. One is metabolic energy is not required. The net transport is from high to low concentration, of the substance being transported. Now, that's an important distinction. Movement of water, that is osmosis, often drags solute with it. This is called solvent drag. Passive transport processes in the kidney depend on three factors. They depend on a concentration difference or gradient, membrane permeability, and blood pressure. Let's look at concentration differences. An increased difference causes an increased rate of transport. This will increase the rate of reabsorption or secretion. Here's a figure to help you visualize the movement. The number of particles are shown in the figures separated by a selectively permeable membrane. The particles are able to cross the membrane. Which shows the greater concentration difference, the upper figure or the lower figure? Well, it's the lower figure, 8,000 on one side, 2,000 on the other side. In which figure would there be a greater rate of transport across the membrane? The lower figure. Instead of moving randomly in all directions, as does occur in diffusion, let's make a model, and let's assume in the model the particles are moving equally at this instant in only 4 directions. For example, from the 4,000 side, how many are moving in each of the 4 directions? 1,000. Let's compare the 4 solutions. You see now the number diffusing in each of the 4 directions is shown. From the 4,000 side, how many particles are moving toward the membrane from the left side of the membrane? 1,000. From the 2,000 side, how many are moving toward the membrane from the right side? 500. From the 8,000 side, how many are moving toward the membrane? 2,000. From the 2,000 side, again, 500 are moving toward the membrane. The bottom figure shows a greater rate. Membrane permeability. Think of holes in the membrane. Now, often transport proteins are involved, such as the aquaporins that allow water to cross. But it's convenient to think of the membrane as having holes. An increased permeability will increase the rate of transport. That is, the holes get bigger. Notice through this hole, 2 particles are moving, 1 in each direction. This will increase the rate of secretion and reabsorption. Decreased permeability would have the opposite effect, decreasing the rate of movement. ADH increases the permeability of membranes to water. What about blood pressure? An increased blood pressure will increase the rate of transport out of the blood from high to low pressure. This will increase the rate of secretion. A decreased blood pressure will increase the rate of transport into the blood. This will increase the rate of reabsorption. What about the active transport processes? Well, they include carrier-mediated active transport. Characteristics of this include metabolic energy is needed. Transport is from low to high concentration. Examples of active processes include the sodium pump, properly the sodium-potassium pump. 90% of extracellular positive ions are sodium ions. Therefore, regulation of sodium takes care of most of the extracellular positive ions. Chlorine, or chloride, is the most abundant negative ion. When sodium is transported across a membrane, chloride follows because positives attract negatives. Therefore, regulation of sodium also takes care of most of the extracellular negative ions. There are other pumps. In general, a sodium pump works like this. Sodium will diffuse into a cell and is pumped out of the cell in the other direction. So we say that the cell pumps sodium from one side of the membrane to the other. What about some details? The diffusion of sodium into the cells of the tubule from the tubular lumen is facilitated diffusion, carrier mediated. The transport proteins are either symport or antiport. In the symport proteins, sodium and a solute, glucose perhaps, amino acids maybe, move in. In the antiport mechanism, sodium moves in and hydrogen ions move out. The active transport of sodium out of the cells is the sodium-potassium pump. Carrier-mediated transport may be passive or active. Glucose transport is an example of carrier-mediated transport. This is largely by a symport sodium-glucose transporter. Let's enlarge a tubular cell and look at saturation. This is one of the important characteristics of carrier-mediated transport. Let's assume that inside the tubule are 3 particles to be transported. The cell contains 3 transport proteins. If one transport molecule to be transported binds to the transporter, the carriers overall are not saturated. If 2 bind to the transport protein, the carriers overall are still not saturated. When the 3rd binds, now the carriers are saturated. The tubular maximum or transport maximum is the concentration of a substance in the tubules at which saturation of the carrier occurs, or it's the maximum rate of reabsorption. The renal threshold is the plasma concentration at which substances will appear in the urine. For glucose, it's around 220 milligrams per 100 milliliters. Normal glucose levels are roughly 70 to 110 milligrams. In this example, the tubular maximum and the renal thresholds are both 3. When glucose levels in the blood rise above the renal threshold of 220 milligrams per liter, the excess molecules are not reabsorbed because the tubular maximum has been reached. They don't find an empty carrier. So the glucose will appear in the urine. The sugar in the urine is a sign of diabetes. A department store analogy illustrates the fate of excess glucose. This, hopefully, will help you understand what we're getting at. Let's assume a department store in a mall is having a big sale, and the entrance to the store is through one of those rotating doors with 4 slots. The hall represents the kidney tubule, the department door represents the blood, and the people are the glucose molecules. Let's assume the door makes 1 rotation per minute. Therefore, as the people are working their way down the hall, how many people can enter the store in 1 minute? 4 can enter in a minute. If 4 are walking down the hall in a minute, all can enter the store because the door has been saturated. In this case, the tubular maximum is 4. If more than 4 are moving down the hall, still only 4 can enter the store per minute. The rest will be jostled and pushed on down the hall and miss the big sale. The renal threshold is 4. Excess are excreted. Substitute glucose for the people, and you can see that the excess glucose is excreted. Here's an exploded view of the nephron. The vascular component includes the afferent arteriole, the glomerulus, and the efferent arteriole. The tubular component includes, in order of flow, the Bowman's capsule, the proximal convoluted tubule, Henle's loop, the distal convoluted tubule, and the collecting tubule. Reabsorption is indicated by arrows out of the tubules, for example, sodium and water. Secretion is indicated by arrows into the tubules, for example, hydrogen ions and potassium ions. Transport processes include osmosis, diffusion, active transport. Let's look at the proximal convoluted tubule. The proximal tubule reabsorbs 80% of all substances which can be reabsorbed, 80% of what has been filtered. This includes sodium by active transport. Chlorine follows the sodium. Potassium by active transport. Calcium by active transport. Glucose by active transport and facilitated diffusion. 100% would be absorbed in a normal person. Amino acids by carrier-mediated active transport. And water by osmosis. Now, this reabsorption of water is called fixed reabsorption, or obligatory, or uncontrolled reabsorption. So 80% of the water that's been filtered is reabsorbed. Urea is also reabsorbed by diffusion. Roughly 44% is reabsorbed. You may think that's odd because urea is a waste product. Hydrogen ions, on the other hand, are secreted into the tubules by active processes. What about the descending limb of Henle? It reabsorbs water by osmosis. It secretes sodium ions by diffusion and chloride ions by diffusion. Urea also is secreted by diffusion. The ascending limb of Henle is very unique because it's impermeable to water. It's one of the few membranes among living systems that does not allow water to cross. It reabsorbs sodium by active transport, chloride also by active transport. Remember, it follows the sodium. The circulation of sodium and chloride down the descending limb, up the ascending limb, and from the ascending limb to the descending limb is a countercurrent exchange mechanism. We'll describe that shortly. The distal convoluted tubule carries out fine control of concentration. It reabsorbs sodium by active transport. This is increased by the presence of aldosterone. Chlorine follows sodium. Water is reabsorbed by osmosis. Roughly 19% is reabsorbed from the distal tubule. This is called variable or facultative or controlled reabsorption. It's increased by ADH. The distal tubule also secretes potassium by active transport. This is increased by aldosterone. Ammonia by diffusion. The collecting tubule reabsorbs water by osmosis. Roughly 0.5% of the filtered water is reabsorbed. Nevertheless, even though it's a small amount, this is critical for regulation of water balance. This is also variable reabsorption, facultative or controlled. It's increased by ADH. Now, remember the net movement of water is toward higher solute concentration. The problem the kidneys face is how to reabsorb enough water to meet the needs of the body. This would produce a hypertonic urine. How can this be accomplished? Can the kidney tubules just pump the water out of the tubules by reabsorption? No, because there's no such thing as a water pump. Water movement across the membrane is strictly by osmosis. It depends on an osmotic pressure difference, that is, a difference in solute concentration. The greater the difference in osmotic pressure or solute concentration, the greater the water movement across the membrane. Osmotic pressure is measured in milliosmoles per liter. The average body osmotic pressure is 300 milliosmoles per liter. The osmotic pressure in the tubules is around 300 milliosmoles or higher. The osmotic pressure of the interstitial fluid must be greater than the osmotic pressure of the tubules in order for a net movement of water to be out of the tubules by osmosis. This is where the countercurrent exchange comes in. For effective water reabsorption, the solute concentration in the interstitial fluid needs to be above 1,000 milliosmoles per liter. How can the osmotic pressure of the interstitial fluid be increased? By countercurrent exchange. The major solutes in the interstitial fluid that contribute to osmotic pressure are sodium ions and chloride ions. How does it work? Well, remember, variable or controlled reabsorption of water occurs in the collecting tubule. Control of sodium concentration and its effect of dragging chloride with it controls osmotic pressure. The lower figure is an enlargement of the ascending limb of Henle's loop. Sodium can be pumped out of the tubule to increase the concentration in the interstitial fluid. Can the sodium pump raise the concentration to, say, 1,100 milliosmoles? No, it can't. The reason is the sodium pump can only generate a force of roughly 200 milliosmoles of osmotic pressure. That is, the sodium pump can't overcome such a great osmotic pressure difference. To raise the osmotic pressure of the interstitial fluid to 1,100, the sodium pump would have to generate 80 milliosmoles of force. The pump is not strong enough to overcome a difference of 800 milliosmoles. So, the sodium pump alone cannot generate a concentration of 1,100 milliosmoles in the interstitial fluid. So how can the interstitial osmotic pressure be increased with the available energy of the sodium pump? This is accomplished by the countercurrent exchange mechanism. It's also referred to as a countercurrent multiplier. It's especially important in a group of nephrons called the juxtamedullary or long nephrons, and a component of the capillary net called the vasa recta. The function of countercurrent exchange is to increase the osmotic pressure of the surrounding interstitial fluid to promote water reabsorption and conserve water. The circulation of sodium and chloride is the countercurrent exchange. The fluids move down the descending limb, around the loop, and up the ascending limb. Then they're reabsorbed from the ascending limb into the interstitial spaces and secreted into the descending limb. And again, the function is to increase the interstitial fluid osmotic pressure with the least expenditure of energy. The longer loop generates a greater increase in the osmotic pressure of the interstitial fluid. By moving fluids in opposite directions, countercurrent, the difference in concentration is not too great at any one point along the flow. Sodium and chloride are secreted into the descending limb of Henle's loop by diffusion. The net movement is from high to low concentration of the sodium and chloride. Sodium and chloride are reabsorbed from the ascending limb of Henle by active transport, sodium pump, from low concentration to high concentration. In this example, the sodium pump only needs to generate a force of 100 milliosmoles osmotic pressure. For example, from 1,000 inside the tubule to 1,100 in the interstitial fluid, 800 to 900, 600 to 700, 400 to 500. Now water can be reabsorbed out of the collecting tubule by osmosis toward the region of higher osmotic concentration. The longer Henle's loop is, the greater the osmotic pressure in the interstitial fluid and the more water that can be absorbed. To maintain the concentration difference, the vasa recta, part of the capillary net, removes the water from the medullary area of the kidney where the Henle's loop are located. Now, more details of water regulation. ADH is the antidiuretic hormone. Diuresis is urine output. ADH increases water reabsorption, thus it decreases urine volume. That opposes the urine output. ADH functions by increasing the size of the pores. Actually, it doesn't do that. It actually increases the production of aquaporins and their placement in the tubular cell membrane. But it's convenient to think of them as increasing pore size. Osmotic pressure difference between the tubules and the extracellular fluid causes net movement of water from the tubules, as we described. The minimum urine volume is the volume of water needed to excrete normal wastes. It's approximately 0.4 of a liter a day. Diuretics increase urine output. Osmotic diuretics increase solute concentration in the tubule. When that happens, it opposes water reabsorption. Thus, more water remains in the tubules. Excess water will be excreted, so there may be a large increase in the flow of water from the body. Examples include diabetes mellitus. In diabetes, there's an increased glucose level in the blood. Increased glucose is filtered into the tubules, leading to increased glucose within the tubules. And because reabsorption can only take care of a certain amount, the excess glucose passes out in the urine. Urine output can increase 4 to 5 liters a day. Drinking salt water also has the same effect. You've heard that if you're cast adrift in a rubber raft in the ocean, you cannot drink the ocean water, the salt water, because you'll actually lose body water. The salt is filtered into the tubules. The tubules alter the osmotic pressure in the tubules. Less water is reabsorbed. More water is lost. So instead of gaining water from drinking it, you're losing water. Another type of diuretic are the enzyme poisons. They block transport of ions and molecules, especially sodium and chloride, in Henle's loop. Increased solute concentration in the tubules, thus decreases water concentration. This opposes water reabsorption and excess water is lost. An example is an antidiuretic called hydrochlorothiazide. Alcohol acts as a diuretic. It does so by inhibiting ADH secretion. This decreases water reabsorption. Caffeine is another. Caffeine dilates the afferent arteriole, which would increase glomerular blood pressure, resulting in an increased filtration. And now you're ready to move on. Part D, urine regulation.